Okay, I'm recording.
I think you need to enable screen sharing for me to share. Okay, cool. All right, is this showing up?
Yeah.
Okay. So today we will go through two different machine learning methods, linear regression and PCA. They're generally quite different and used for different purposes, but might be a good fit together because one time I got asked to compare them in an interview. So here we are. First off, let's start with linear regression. It's a very basic regression method, but it's actually used a lot in industry. Regression is basically just taking in a bunch of inputs and predicting real number values as your outputs based on the inputs. So our inputs are these X and Y pairs, where X is your input data, and we define that as a vector that is D plus 1 dimensional. So the first value is going to be 1, just like how you have a y-intercept that's just a constant value. And then the rest of these are going to be your x values, and then w is essentially going to be the same as like your coefficients in like a y equals ax plus b equation, where w is just a but higher dimensional. So what you would do is you multiply w and x, and this is sort of like the ax portion, the ax plus b portion in an equation, since this 1 here is multiplied by w0, which is the equivalent of the y-intercept.
Can you, 1 second, can you like zoom in? So like,
oh yeah,
it might be a little small for people who like watch it in recording. Yeah, that's good, that's great.
It's better, okay.
Yeah.
So in the end, what you want is you want to come up with this predictor function, f or f of x, where it's just composed by your weights or features multiplied by your input. I'm doing transpose here because vectors are supposed to be vertical. These are supposed to be column vectors, but you do this transpose times the input, and that gives you an output, y star. I'm going to be using asterisks here, both for modifying a variable as well as multiplying down here. So it's going to be a little confusing since I don't know how to tech in Colab Notebook. But essentially, the output of this f function based on some input is going to be what we call y star. Here, I'm going to be using capital X to indicate that we have a data matrix as our input. So instead of having a d-dimensional column vector, it's going to be an n by d matrix. So each row is going to be 1 data point. So we'll have n data points that are d-dimensional. So, and then from here on out, I'm just going to include this 1 as like part of the d. Since it's easier to say. And our goal is to predict y values optimally, of course, using what we call empirical risk minimization. So there are two schools of thoughts when it comes to machine learning: empirical risk minimization and maximum likelihood estimators. So this is all about minimizing the error based on the differences between what your output is and what the actual output should be. So like, I guess the true output is a better way to put it, which is this y here. And maximum likelihood estimation is about estimating the features that are the most likely to be true features based on the data that we have seen. It's a lot less straightforward than ERM here, which is what we'll be using for linear regression. Maybe I can talk about that in a different video. So here, what we're minimizing is the error. In this case, it's represented by this loss function. So loss function is just the error of your predictor function f based on the differences between the true y and the y that you predict. Generally speaking, for regressions, there are two different kinds of loss functions. Quadratic loss, which is taking the sum of the squared differences. It's also called mean squared error because you're squaring the errors, and then at the end you divide it by n, the number of data points you have, to get your average squared error or mean squared error. The other loss function you have is absolute loss. So this is just taking the absolute value between, or absolute value of the differences and then summing it. And so quadratic loss is also called L2 loss because it's kind of like the L2 norm, like Euclidean distance, whereas absolute loss is called L1 loss. And the main difference between them is that L2 loss will penalize large differences more. So because of the way squaring works, it really tries to make sure that this line of best fit, this predictor function f that you have, doesn't have huge errors on one side versus the other, since it tries to make sure that all the distances and the errors between points are as close to each other as possible. Kind of rambling here. But this also makes it less robust against outliers, since if you have a couple of outliers in your data, those will be the big differences that normally, like if you had a human engineer the features for you, you might want to ignore. But in this case, it will really try to overcompensate for those outliers. And so that might screw it up a little bit. But the benefit is that under certain circumstances, you will have only one solution. Whereas if you take absolute loss, you might end up with multiple solutions, since it's just taking the absolute value of the differences. But absolute value is, or L1 loss is used elsewhere in other regression methods, like lasso, for example. There's some other benefits it has for feature selection. Since a weird phenomenon that occurs with L1 loss is that a lot of features tend to go to 0. So a lot of these values will end up going to 0, and you end up with a simpler model with less features. But for linear regression, we are going to be using L2 loss. Some might even call linear regression least squares regression for this exact reason. So our loss function is going to be the average of the sum of the differences between what we predict and what the actual value is squared for all data points. And we want to find the set of features or weights that will minimize this loss function. And so there is an analytical solution for it, and the math behind it isn't overly complicated, but it would be a pretty big tangent. So I'm not going to go over it here. I'm just going to be listing the formula out. It's this one giant matrix operation. And so that gives you your optimal weights. And then if you were to multiply by our input x, this is essentially just W star times x. But the terms had to be rearranged a little bit to make the dimensions work out. So a note on this analytical solution is that you usually don't see this in machine learning. This also only works if this linear regression is truly linear. As in, sometimes instead of using x, you can actually transform them first into what we call h of x, which would be human engineered features. So for example, say you would take seasonality, for example. There's natural sinusoidal patterns in the data that is very easy for humans to see, but kind of hard for a machine to see. And so once we add sign of, say, X as one of the features, this analytical solution won't work anymore. So unlike PCA, or I guess for linear regression, we'll just completely be using sklearn instead of doing it by hand, since this is pretty studied and I'm pretty sure you'll never have to do it by hand. I didn't write this code myself. This is a pretty well like studied piece of example. This is from the sklearn official website. And I'm pretty sure if you take CS 446, they use this exact like same piece of code in their lectures. So what we'll be doing here is we're getting diabetes data, and we will be taking just the first feature and finding out the best weights to multiply this data point by to get the optimal, I guess, Y. We're just loading some data sets here, getting the X's and the Y's, extracting out just the first column in X's, splitting it into training and testing data for both X's and Y's. We'll be doing an 80-20 split. So here, this -20 at the second part just means that we'll be taking the first 80%. This is the bottom 20% of the data. Splitting Y accordingly, getting a linear regression object, fitting it with our training data, and then make our prediction with the data of our, with the X part of our testing data. And then we can get the coefficients, since we've already trained the model up here, get the mean squared error by taking the differences between what we predict and what the actual Y is, and also getting the, what's it called, like the R-squared score of our prediction and the test data. So then we plot these against each other, and we find that for one feature, the optimal coefficient is 938. We get the mean squared error, and we have a coefficient of determination. This is the R-squared score of 0.47. And just quickly plotting some points here. This is our line of best fit. Notice how there aren't like any, or generally speaking, the points are kind of here, but there are like gigantic outliers that the line probably tried to minimize. Otherwise, I think it should be more like closer to this. So we can also use multiple features here. So double quotes versus single quotes. So if we were to do this again, now we are getting a bunch of them. Okay, the scatter plot doesn't work, but we got the coefficients. And these would be the updated coefficients if we were to use 4 features instead of just 1 feature. I had this working before. Whatever. Any questions so far?
Okay, so isn't there also like ridge regression, which is also L2 loss? So what's like the difference?
Yeah, so there is also ridge regression, and generally speaking, it's, or I guess I can just go over all the regression methods quickly here. So linear regression is the most straightforward one, which is what we see here. Ridge regression is sort of a multiple regression. And we also have a lasso regression, which is like absolute shrinkage, where we try to select some of the features. So for a simpler model. And
I'm pretty sure like
ridge regression is sort of like a variant of linear. I'm pretty sure it's just like multiple linear regression. if that
Well,
makes
like
sense.
I'm pretty sure like linear regression includes regression and lasso regression, like linear regression. And so there's
Really?
like, yeah, yeah. So because multiple regression is still ridge regression, right? Multiple
Yeah,
linear
multiple
regression,
regression is like ridge regression. I thought linear
but
regression was
still,
sort of like a simple case of ridge.
I think like linear regression like includes ridge regression and lasso regression. They just use different losses. I'm pretty sure that's.
Oh,
But like
yeah, yeah,
there's
yeah. I think you're
OLS
right. You're right.
regression. There's OLS regression, which is I don't know.
Like ordinary least squares, right? I think that's
Like,
what the O stands for.
but here we use. I'm pretty sure this is a ridge regression algorithm because it's not solving the. Sklearn doesn't solve it analytically.
Oh, yeah, I guess in that case, then this would be ridge,
Yeah.
right? They're probably gradient descending.
Yeah.
Yeah. Oops.
But
Okay.
it's yeah, that's good.
Yeah.
Makes sense.
Okay. So next we'll go to PCA, principal component analysis. It's used for generally two different purposes: dimensionality reduction and data visualization. So PCA is sort of based on this linear algebra concept called change of basis, where a basis is a set of vectors that define a coordinate system. So for example, our coordinate system is this basis where each point we have, if we were to multiply by this, we get the same point back because our points are defined in this coordinate system. But we can change it to be in a new coordinate system through some matrix multiplication math. And the reason why we want to put it in a new coordinate system is that our data is too big and complicated, and sometimes we just want to find, we want to project our high dimensional data into a lower dimension by picking out the features, or I guess in this case, the a couple of these that actually make the most difference in our data. And with PCA, what you'll get is a few vectors that define new axes, and each one is what they call the direction of greatest variance. And this will make more sense as we go on. So I guess here's a cool visualization of PCA. I think 3D is hard to see, so we'll stick with 2D. And here we're just seeing that we're projecting this data into a new set. And I guess right now we're sort of going from 2D to 2D, but it can be used for visualization, kind of like this. If you're keeping all the principal components and your data was already simple. Yeah, but here you see that we are just changing our coordinate system. In this case, we're going from this diagonal to what would be visualized as horizontal. And so the way we would do this is, say we generate, say we just have these data points, right? And same thing as before, this is m by d. These are 5 three-dimensional data points. And say this is too complicated and we want to, and too computationally expensive to figure things out with. We want to extract the 2 dimensions that make the most difference in our data. And so first, so we can get the mean here, take the covariance matrix. So this here is just sort of like a math of how to do PCA by hand. And you can also just do this with sklearn. But if we were to do it by hand, you would be taking the mean of each column, so of each dimension across all the data points, centering it, which means that you want the mean of each column to be 0, so you just subtract each data point here by the mean. Doing a matrix multiplication with itself to get the covariance matrix, and then finding the eigenvectors and eigenvalues of this covariance matrix, and then doing a dot product, and then these are our principal components, which is almost the same as the ones that sklearn will give us. So this first eigenvector is the same. The second one is actually different, but it differs by a factor of -1. So the way you figure out which eigenvectors are the principal components, or I guess they're all principal components, but you want to order them so that you get vectors, which are essentially directions, into the direction of maximum variance. And so you want to order them by the value of their corresponding eigenvalues. And this works because even though eigenvectors are not unique, eigenvalues are unique. If you take like a class on it, sometimes they'll say all your eigenvectors should be unit vectors. So they're across all the dimensions, the length is 1, which just means that you might end up with one of 2 different solutions, like a positive version and some negative version. And so there isn't like a whole lot to say about the math behind it. I more so want to talk about why these are called like directions of maximum variance. So if you were to like take a math class on this, they'll say PCA is sort of like projecting your data onto a p-dimensional ball, which is, you know, like in 2 dimensions, that's a circle, in 3 dimensions, that's a sphere. And in p dimensions, it's some abstract thing you can't really visualize, but it won't be like a perfect circle or sphere in that pth dimension. It will be sort of like an oval thing in whatever dimension that is. And if we were to visualize this in 2 dimensions, you know, an oval would be something like this, and our first eigenvector will be this axis, the fat part of the oval, because that is the direction in which the data varies the most. So this PCA is really like a way to transform our data so that we select out the parts that matter the most in determining what makes one data point differ from another. And yeah, so some notes here about like whether you should center the data.
I have a quick question. Like, what I see 5 rows and 2 columns, but there are 3 input variables. So like,
oh, it's 5 by 3. So this is yeah, it's
that's weird. I usually use columns with variables.
Oh yeah.
Wait, yeah. Oh, it's because I use pandas. That's why.
Oh yeah. I guess it's just personal preference. Just depends on your data.
Okay. Yeah. All right then.
Coming from like if you do CS446, I'm pretty sure they always want like each row to be 1 data point.
Okay. Yeah. Never mind. Okay. So we're looking at those, and so you choose. So like the ones like. Is it like the magnitude of the what do they call it? The magnitude of the eigen something, like on the left side, right? Like, how do you know which ones to take out? Like, can you like repeat that?
Okay, yeah. So essentially, you will get. Okay, so here I guess are all of the eigenvectors and the corresponding eigenvalues. So Okay, I think, yeah. So W here, these are the eigenvalues, and we see that we have 3 different eigenvalues. And here, the way you would think about these is that each one of these is a direction in which the data varies. And this is the one that will matter the most, followed by this. And you see that this here in comparison doesn't really explain as much variation, and that the majority of the data variation is explained in these 2 different columns. So here I'm just sorting it and taking the top 2, so which gives us these. And then this dot product here just literally multiplies our data array by these eigenvectors, and this is our like new data.
Okay.
And then obviously here it's going to differ a little bit because eigenvectors are not unique, so they might have like, you know, positive, positive, negative here, but the values are the same, scaled. Does that make a little more sense?
Yeah. Okay. So you, what's the 5x2 thing? Like the new data. So and then you take that new data and like take some of them out, right? Like,
yeah, you would just be processing off of this new data instead of the old data.
oh, so you don't get rid of anything. You don't get rid of any.
This is already like picked apart.
Okay.
If that makes sense.
Yeah.
Yeah. So this is just the whole like picking apart process, and then in the end, you go from this to that.
Oh yeah, that makes sense.
And then you can also actually like plot principal components as lines, because, you know, vectors are directions and you can just keep on extending them. So what's the difference between like a line that you get from linear, I guess in our case, ridge regression versus like the first principal component? So I actually got asked this in an interview, and here's a handy little website that gives us visualization. But essentially, we get that when you try to fit a linear regression, you're taking x with respect to y, and you're minimizing the difference between the vertical difference between the points and the line, right? So you go straight down here. Alternatively, if you really want, you can predict x with respect to y and get a different one where it's minimizing this, where it's minimizing the horizontal distance between a point and the line, going like straight across. If you were to plot the first principal component, what you get is kind of something right in the middle. So it's minimizing the legitimate shortest distance between the point and the line. So like the orthogonal distance. And yeah, you can put them all 3 together, and that they're all a little bit different. And yeah. And I guess like part of this can be explained by linear regression just care about y, you know, based on what x is, whereas PCA is sort of looking at x and y as a whole and trying to determine like where they differ the most. So in this case, it's minimizing the orthogonal distance.
Okay, so yeah. Did you learn all of this in 446?
For the most part, you learn all of this in 446. They don't talk about this. I actually like completely choked on the interview. I looked it up afterwards.
Oh, okay.
Yeah.
I wonder, like, I already saw this problem before, to like skip problems, you know?
Mm-hmm.
That'd probably be a terrible idea though. Like when someone asks you if you like seen a problem before, you can say, "Oh, I already saw that before, so we can skip it. Let's skip it." You know?
Yeah.
No, I'm just kidding. Probably.
I mean, I would never say that I've seen it before. So.
Yeah, and if I saw one that I actually knew, I'd probably say that I never saw it before. So I can do it easily.
Mhm.